Space is vast and seemingly empty, but within the darkness there are regions teeming with the raw materials for stars and planets. These are the stellar nurseries, also known as molecular clouds. Imagine colossal clouds of gas and dust stretching for light years. They are cold and dark, dominated by hydrogen and helium, the most abundant elements in the universe. These clouds also contain traces of heavier elements, the remnants of past generations of stars. Within these cosmic cradles, the adventure of planet formation begins. These clouds seem serene, but they are actually dynamic environments. Turbulence swirls within them. Gravity plays a constant game of push and pull. The stage is set for something incredible: the birth of stars and their planetary systems. The universe is constantly evolving, with new worlds emerging from the ashes of the old. And it all starts in these stellar nurseries. The universe is filled with these stellar nurseries. They are scattered throughout galaxies like seeds of cosmic creation. Our own Milky Way galaxy is home to many such regions. One famous example is the Orion Nebula, visible to the naked eye as a fuzzy patch in the sword of the constellation Orion. The Orion Nebula is a spectacular sight. It reveals the dynamic processes of star and planet formation in action. Stars are not born quietly. They burst onto the cosmic scene in dramatic fashion. One catalyst for star birth is the shockwave. Imagine a supernova, the explosive death of a massive star. This cosmic blast sends shockwaves rippling through space. These shockwaves can slam into nearby molecular clouds, compressing the gas and dust within. This compression is critical. It increases the density of the cloud, making gravity's pull stronger. As gravity takes hold, the cloud begins to collapse inward. The once diffuse material starts to clump together, forming denser regions within the cloud. These dense regions become the seeds of new stars. Gravity continues to draw material inward, and the core of the collapsing cloud heats up. This process of gravitational collapse is not a gentle one. The collapsing cloud fragments into smaller, denser clumps. Within these clumps, individual stars begin to take shape. As more and more material falls onto the nascent star, its core temperature and pressure soar. Eventually the core becomes hot and dense enough to ignite nuclear fusion. Hydrogen atoms fuse together, releasing enormous amounts of energy. A star is born. The birth of a star is rarely a solitary event. As the collapsing cloud of gas and dust forms a star at its center, it also creates something remarkable around it: a protoplanetary disk. Imagine a vast, swirling disk of leftover material encircling the newborn star. This disk, composed of gas, dust, and ice, is the birthplace of planets. It is a cosmic womb, nurturing the formation of planetary systems. The protoplanetary disk is not just a flat, static structure. It is a dynamic and evolving environment. The young star at the center exerts a powerful gravitational pull on the disk, shaping its structure and evolution. The disk is also influenced by the star's radiation and magnetic fields. Within this chaotic dance of matter and energy, planets begin to form. The material in the disk is not evenly distributed. Closer to the star, where temperatures are higher, the disk is dominated by gas and dust. Further out, where temperatures are colder, the disk contains ices, frozen water, methane, and ammonia. These ices play a crucial role in the formation of giant planets. The composition of the protoplanetary disk varies from star to star, influencing the types of planets that can form. The protoplanetary disk is a chaotic place. Tiny particles of dust, remnants of the original molecular cloud, are constantly colliding with each other. These collisions are initially random and chaotic, but gradually, a remarkable process begins to unfold: accretion. Imagine these dust grains, no bigger than the width of a human hair, sticking together upon impact. Over time, these tiny particles grow larger, forming pebble-sized objects. This process of accretion is driven by electrostatic forces. The dust grains carry static charges, much like the static cling you might experience with clothes fresh out of the dryer. These electrostatic forces cause the grains to attract and stick to each other. As the pebbles grow larger, they exert a stronger gravitational pull, attracting even more particles. The protoplanetary disk is not a peaceful place. Collisions between these growing pebbles are common. Some collisions are destructive, shattering the pebbles back into smaller fragments, but other collisions are constructive, leading to the formation of even larger objects. Over millions of years, this process of accretion transforms the dusty disk into a collection of larger bodies. Section 5, Planetesimals, building blocks of planets. As the pebbles continue to grow, they eventually reach a critical size, approximately 1 kilometer in diameter. These kilometer-sized objects are called planetesimals. Planetesimals are the building blocks of planets. They are large enough to exert a significant gravitational pull on their surroundings. This gravitational pull allows them to attract and accumulate more material, growing even larger. The early solar system was a crowded and chaotic place, with planetesimals whizzing around the young sun. Collisions between planetesimals were frequent and violent. Some collisions resulted in the destruction of both objects, but other collisions led to the merging of planetesimals, creating even larger bodies. Over time, a few dominant planetesimals emerged, clearing their orbits of smaller objects. The formation of planetesimals is a critical step in the planet-forming process. These objects represent a significant increase in size and mass compared to the original dust grains. They are the seeds around which planets will eventually form. The distribution of planetesimals in the protoplanetary disk will influence the size and location of the planets that eventually emerge. Section 6. Protoplanets, a tumultuous youth. The largest planetesimals, those that have managed to survive the chaotic early stages of planet formation, continue to grow by accreting smaller objects. These massive bodies, now tens or even hundreds of kilometers in diameter, are called protoplanets. Protoplanets are the precursors to full-fledged planets. They are still undergoing significant growth and evolution. Their surfaces are bombarded by a constant rain of planetesimals and other debris. The process of protoplanet formation is a tumultuous one. Collisions between these massive objects release enormous amounts of energy, heating up their interiors. The gravitational pull of protoplanets can also stir up the surrounding disk, creating spiral arms and gaps in the material. These interactions between protoplanets and the disk can influence the orbits of other objects, shaping the overall architecture of the planetary system. As protoplanets grow larger, their gravitational pull becomes stronger. This increased gravity allows them to capture and retain volatile materials, such as water ice and methane. These volatiles, which would have been vaporized closer to the star, can condense and accumulate on the surfaces of protoplanets in the outer regions of the disk. The composition of a protoplanet's atmosphere and surface is determined by its location in the disk and the materials it accretes. Section 7. Shaping the planetary layers. Deep within protoplanets, intense heat melts the interior. This molten material undergoes differentiation. Heavy elements sink, forming the core. Lighter elements rise, forming the mantle and crust. Differentiation shapes planetary evolution. It influences magnetic fields and tectonics. Larger planets retain heat, driving activity. Giant planets radiate more energy than they receive. Section 8. Magnetic fields and atmospheres. As planets solidify, they develop magnetic fields and atmospheres. Earth's magnetic field, generated by molten iron in its outer core, shields us from harmful solar radiation. This field is essential for life. Jupiter and Saturn have powerful magnetic fields from metallic hydrogen. Atmospheres are shaped by volcanic outgassing and comet impacts. Earth's nitrogen and oxygen-rich atmosphere supports life. Magnetic fields create auroras by interacting with solar wind. Studying these fields helps us understand planetary evolution and potential extraterrestrial life. Section 9. A new solar system emerges. Millions of years have passed. The once chaotic protoplanetary disk has transformed into a more ordered system. Planets have cleared their orbits, sweeping up most of the remaining debris. A new solar system has emerged from the cosmic cloud. The central star shines brightly, its energy sustaining the planets orbiting it. Each planet bears the scars of its formation impact craters, volcanic plains, and perhaps even the ingredients for life. The planets are not static. They continue to evolve, influenced by their interactions with the star and each other. Some planets may migrate inward or outward, their orbits shifting over time. Giant planets can shepherd smaller planets, shaping their orbits and preventing collisions. And over vast cosmic timescales, even stars themselves evolve, eventually exhausting their nuclear fuel and ending their lives. The formation of a solar system is a testament to the power of gravity, time, and the intricate dance of matter and energy. From the tiniest dust grains to massive planets, the universe is constantly creating and evolving. And as we look up at the night sky, we are reminded that our own solar system, with its diverse planets and the potential for life, is just one of countless planetary systems scattered throughout the vastness of space.